Good morning.
Good morning.
Okay.
Morning.
Let's walk through the last of this stuff. Okay, so to be fully computational, we want to be able to do computations. We want to be able to do assignment, selection, if then else, and some form of repetition, either iterative like for loops, while loops, or recursion. So part of this is about just showing you how to utilize the beta reductions and alpha reductions. And part of this is about showing you that this is a fully computational system. We covered addition, the add one function at least. And last time, and so I'll review that quickly. The author, Rojas, goes on and actually generalizes to addition and also to multiplication. We don't need to cover that. I'm not going to ask you to get that in depth in doing the manipulations for lambda calculus. It's ugly, you know, it's pretty bad, and it's easy to lose track of where you are and make a mistake on where you are in terms of precedence with the parentheses. But if you walk through, in fact, it's so ugly, he says, you know, this is left as an exercise to the student, right? That's a clue right there. But you can find worked examples if you have interest in them. So I'll walk through that. Then we'll go through just the definition of the Boolean functions, values and functions, and then show recursion. And so again, the system is there, this thing is so abstract, there is no concept as integers defined within the basic system. The basic system is just an expression, can be a variable, a function, or application. So the trick is, how do you come up with representing numerals? And this is the method. We start out with 0, and then we say 1 is the successor to 0, and 2 is the successor to 1, and 3 is the successor to 3. And that gets represented by continuing to do nesting on this, this form here, this sc.z. Now think about what sc.z does, by the way. Lambda sc.z is a function of two inputs, s and z. It throws the first one away and then just gives you back the second one. 1 is a function of s and z that applies the first to the second. 2 is the function of s and z that applies the first to the result of applying the first to the second. So you can kind of see they're building up this notion of 1 is the successor to 0, 2 is the successor of 1, as long as they can come up with a successor function. And they do. So the successor function is this kind of a mess. And after you work with it a couple times, you see all of these are cheap tricks, really. The cheap trick here is that this is a function of 3 inputs, w, y, x. And what do? They put a y outside and then repeat w, y, x. Now remember, I don't put the spaces in here. Most authors don't. But this is w applied to y applied to x. Let's see. So they're putting that additional y out there with the parentheses. Gosh, it looks like they're setting up for this kind of a trick, right? Putting that s out there inside of the parentheses. And that's exactly what they're doing. So if we apply the successor function to 0, there's 0. Well, let's see, lambda sz.z goes in for w. So now we have w, y, x, y, lambda sz.z applied to y and x. But remember, lambda sz.z is a function of 2 arguments, 2 inputs. And what are the 2 inputs? Y and x. So you do the first one. Y goes in for s and disappears. X goes in for z, and all you get is x. And now you have this form, lambda y x, y parentheses x. Because we only care about structure, we don't care about the actual variable names. That's the exact same structure as ysz.s parentheses z. And after you do this a couple times, by all means, play with it on your own. Now do it for, that's the numeral 1. Do it for the numeral 1, and then do it for the numeral 2. And you'll see what this pattern does, this cheap pattern here. All it does is it puts the y out front, and then it applies, remember, in this case, it applied 0 to y and x, which created the 1. And then if you apply this to 1, it's going to apply 1 to y and x, which effectively is going to create, when you include this external y, that creates the numeral 2. Does it seem odd to you that numerals are also functions? We don't normally think of numerals as functions, right? It's just a pattern. Remember, it's just a pattern. Then, heck, that's just a pattern, right? The symbol 1. When we apply successor to 1, same trick. Now, we got this last time, right? Successor to 0 was 1, so that's 1. Same trick. We're going to put this in for w. There it is. The w goes away, and now we have a function of 2 inputs, y and x. But along the way, we got that extra y outside the parentheses. See the cheap trick there? You get that extra y outside the parentheses, and what happens? You are building up this nesting of parentheses. And since the first argument to this internal function, right, inside here, we're going to do the beta reductions again, lambda sz dot sz is a function of 2 arguments. And because now we have this s outside the parentheses, when we put the first argument in, which is y, we get a y outside the parentheses. When we put the x in for z, we just get x. But since we've already had, let's see, that gives us 1 y outside the parentheses. That trick gave us 2 y's outside the parentheses. So by the time we're done, we have yx. But since we don't care about the variable names, we can always revert to sz dot sc like this. And that's 2. This is also 2. It just looked different because we originally defined it in terms of s's and z's. If we were to do this again, we would find that we already have 2 s's outside the parentheses. When we did the cheap trick, we would get this y outside the parentheses. We would apply this SSZ to YZ, which means both of these S's turn into Y's, the Z turns into an X, and all of a sudden we've got 3 Y's and an X, or the numeral 3. Your homework, I've filled in, it's up, and it's simpler than this, or the intent was for it to be simpler than this. If you really want to get your eyes crossed, look at how multiplication is performed. All right, now let's move on to, well, first of all, let's pause for questions. Do you believe that math exists, I guess? Are you buying into it?
I'd say yes.
Okay. A lot of people have said yes over the last 90 years, so that's good. It's a safe answer. Okay, now let's move into the Boolean world. Think about how you use if then else statements in programming. If then else. What does that mean? It is highly annoying. That's right. And that's why, you know, people aren't doing their work in the Lambda calculus, right? There's a reason why you didn't do your 8th grade algebra in Lambda calculus, because it's highly annoying. It is a system, though, by which you can make formal proofs about properties of mathematics, specifically properties of functions. And the bottom line is that the church comes up with is, not everything can be represented in this fully computational system. Therefore, not everything is computational. Okay, so how do you interpret that statement? An if then else. When you're telling people about an if then else, how do you explain it to them? Have you? If true, do this, else do that. Yeah. I'm gonna frame it slightly differently. I'm gonna say we have two things. The first and the second. If the Boolean test is true, take the first and throw away the second. If the Boolean test is false, throw away the first and take the second. If I framed it in terms of a function, that's Java, right? Or return, I could say return, right? Fair enough? I'm framing it this way because if we wanted to create a lambda for true, a lambda expression for true, how about we take in two inputs? Remember, I'm using capital L here. Two inputs. And if this thing is true, I take in two inputs, and what do I give back? The first one. So this is the lambda expression for true. And guess what false looks like? Ignore the first input and return the second. No, don't do that. Oh my, no, that's not what I wanted at all. Microsoft does things I never even knew it could do. And it only does it when I accidentally trigger it. One time my dog walked across the keyboard and my screen turned 90 degrees and it took me half an hour how to figure out how to get it back. All right, so that's what we're going to expect. The lambda expression for true, which is a value, but notice that value is also a function, is that, and the lambda expression for false is that. And if you think about it, it actually makes sense. Because what do you do when something's true and an if then else? Take the first, throw away the second, ignore the second. What do you do when it's false? Ignore the first, take the second. So there we are. Taking the first, ignore the second. And then the and, or, and not, the three basic operators in Boolean world are represented this way. And they look a little odd. But what's happening here? The and, it's kind of interesting. What they're doing is this. They're embedding a false in there. Now, why would you embed a false in an and operator? Because basically what you need to make sure of is that both halves of the operator are true, but the default case would be false. And for the or operator, they embed true in the middle of the or operator. Why would they do that? Because in either case, it's true. And what's the not? Lambda x ft. Now, let's start with the not, actually. Think about how this works. If I say, I'm going to say that true is equal to lambda uv dot u. I'm going to say that false is equal to lambda uv dot v. And I'm going to just use shorthand here. If I say true is applied to 6 and 8, that's right, 6 and 8 are two arguments. I'm not going to write out luv.u. I'm just going to say, hey, we know what true does. It takes the first and throws away the second. So if I apply true to 6, do you agree, true applied to 6 and 8, do you agree that I would get 6 back? That makes sense,
yeah.
Right? Because all we're doing is taking the first and ignoring the second. So let's look at how not works. Not is equal to lambda x dot x false true. Now let's apply not to true. What should we get? We better get false, right? We better get that. Well, how would you get that? Well, not applied to true looks like this. lx dot, I need to use parentheses, x f t applied to true. If I do the beta reduction, what do I get? How do I do it? Can I do it? Here's my application. That's one expression, and that's one expression. So it's application. Can I use a beta reduction? In other words, the expression on the left is a function, therefore I can use the beta reduction. And what does the beta reduction say to do?
Wouldn't you just be left with true, false, true in this
We
case?
are left with true, false, true, right? So we're left with true, false, true. So the beta reduction says, hey, this is an argument of a function of one argument. X is the input. And when we do the beta reduction, we get rid of Lx dot, and everywhere we see an X, we replace it with T or true. And so I get true, false, true. Now remember what true is. What did we say true was? Isn't it a function that takes in two arguments? Keeps the first and throws the second one away. So when I apply,
Clever.
Pardon?
I said clever.
Yeah, isn't that cute? So when I apply true to false and true, I keep false and throw true away. Now what happens if I apply it to false? I get ft, and what does false do? It throws away the first and keeps the second. So not true is false and not false is true. It's weird that this stuff works. What if we apply and to true and true? What should we come up with?
True, right?
True.
We better come up with true, right? or there's a lot of math books that are wrong. So what is and? It's lxy dot xy, and I'm just going to put a true here instead of that lambda uv dot v. I'm sorry, a false. Instead of that lambda uv dot v, I'm just going to put a false there. And we're going to apply that to true and true. And so let's see. Here's an expression. There's an expression. I can apply the beta reduction rule. Remember, this is basically a function of two inputs. And the first input is going to be true. So when I do my first beta reduction, I get Ly because I get rid of the X. Everywhere I see an X, I replace it with T. So that's T, Y, F. And now I still have another T out here. Now I have on the left-hand side a function still of one argument, which is Y. I can do another beta reduction. I get rid of the Ly dot, and everywhere I see a Y in the expression, I replace it with T. So that's TTF, which looks a little better if we write it this way. Whoops, no, don't change it, TTF. Okay, so now what does this say again? That's an argument of two inputs that keeps the first and throws the second away. So when we take the AND function and apply it to true, true, we get true. What happens if we apply it to false? True, false. We should get false, right? This is going to look the same, except that's an F. And then when I do the next one, I get TFF. And what does T do? It takes the first and throws the second away, so I get F. And this is things where things get really clever. If we switch it, it should still be false, right? And it is, because what does false do? It's going to keep, let's see. Now that gets Ly, and it's FYF applied to true, which then becomes FTF. But what does F do? Ignores the first and keeps the second, so we get F. I can't see your faces, but I imagine you all like amazed, okay? That's just my, it pleases me to think that.
I'm kind of amazed right now. I think I'm piecing it together.
It's pretty weird. And I think this actually is a little clearer to understand than the addition stuff, and certainly the multiplication stuff, because you get so bogged down in the weeds with the addition and multiplication.
Definitely.
And what they're doing, so you see what they did here with the and, this cute trick of putting the F at the end, is they're embedding that F in there, so that if there's ever an F in the expression that you're applying it to, it doesn't matter if the first location is an F or the second, but and applied to F in true and applied to true and false, they're both going to rely on that F on the end. If it's true and true, that F never comes up. But if it's true and false, the second F will work. If it's false and true, that's the F that makes it work. And the same cheap trick applies here. They're kind of putting that true in there. Why? Because it's going to be the default value that you get. If the first argument is true, what's going to happen? We're going to grab the first thing, which is true. So right away, you get the default argument. If the second was true, then that Y is going to be replaced by true, and you'll have true, true, so it won't matter. And if they're both true, it won't matter. We can run through that quickly enough. Lambda xy dot x true y. That's or. So if we apply or to true and false, okay, lost the ability to capitalize. Now what should happen? What do you know the response should be? It should be true, correct? Well, let's see, that's LXY, X true Y applied to true and false. I do the first beta reduction and I get Ly dot true true Y applied to false. You can already see what's going to happen. That true is going to grab the second true. Doesn't matter what the second argument is, because I end up with true, true, false, which I'm going to write this way just so we can. And what does the true do? It grabs the first one. switch it around, and we get ly dot fty, this time applied to true, which means it's going to be ftt, and what does f do? It grabs the second one, which is still true. And then lastly, the only way we can get false out of this is if we do that. F, and what does false do? It grabs the second one. So we have and, or, and not. The author goes on to do actual Boolean tests where you actually complete the full if then else statements, or the if then else expressions. We don't need to do that. I just want to convince you that it exists. Okay, so that's these examples here. So we have numerals, we have math operators, we have Boolean operators. The last thing we need, so we can do selection, the last thing we need is repetition. And we get repetition through recursion. The thing that makes recursion work is the Y combinator, and you're going to see again, it's everything here is just a cheap trick. Just a matter of making portions of things. So basically what you're doing with recursion is this allows you to make copies and after copy, after copy, after copy of expressions. And then of course, since those expressions can be functions, what that means is each of those copies can perform an action. So you get to do actions over and over and over again in a recursive way. And you guys know what recursion means in your programming classes, right? It's the same idea here. What does recursion mean in programming?
Effectively calling a function within a function until it reaches a base case with different inputs each time.
Right, and not just calling any old function within a function. What function do you call?
The same function
Same function, right. So it's when a function calls itself over and over and over again. And the way this works is through this interesting looking thing, the Y combinator. Now notice, let's do our free and bound variables. Is this X bound?
Yes.
Yeah, and it's bound right here. How about this X? Is it bound? Yes, and it's bound right there. How about these Y's? Is this Y bound?
Not by the inner Lambda statement, but
No.
the outside one.
Right, that's right. Not by the inner, but by the outer. So what's going to happen is if we apply this to something, and people for some reason use R, I guess, for recursion. If we apply this to R, what's the first thing that's going to happen? We're going to have this whole expression applied to R, and because we always work from the outside in, that means that this is really a function of one argument, Y, and everywhere where you see a Y in here, we're going to replace it with R. But because this is an expression and that's an expression, we have application. And because this is a function on the left, we can apply it to the expression on the right. And so what's going to happen is first we're going to chunk R in there, and then we're going to start to make copies. So the outer FY, that thing, is really saying, hey, tell me what you want copied, and I'll just make 1,000,000 of them. There really is, the way I present it, there's no way to turn it off. So Miles was right. When you do recursion, you need to get down to a base case so you can stop it. You know, anytime you do repetition in any programming language, whether it's iteration or whether it's recursion, you need three things. You need a way to start it, and you need a way to stop it. And you need progress towards the stopping condition. The way this is framed, there's no stopping condition. However, as you could imagine, if you define an R cleverly enough, with a function that say continually moves towards some end condition, and we already have if then else's, then that can be incorporated. But if you think it's ugly the way it is now, obviously it gets much uglier. So we're just going to stick with R and prove that we can make as many copies of R as we want. And it looks like this, which I can walk through in our little notepad if we want. But Y applied to R. This is just the original expression, the original Y combinator applied to R. And how do we, okay, so we have beta reduction. That means that because this is a function of one input, Y, I'm going to get rid of lambda Y dot. And everywhere I see a Y inside here, I'm going to replace it with R. So now I have this interesting pattern, lambda X, R, X, X, twice. But the one on the left is a function, so it can be applied to the one on the right. So what happens when you apply the one on the left to the one on the right? Well, let's see, that's a function of one input, and all it does is it makes two copies of the thing that you're putting in there. What are you putting in there? Lambda X, R, X, X. So that means you have R, that's that one, and then lambda XR XX. I'll do it on a notepad so we can, but now you can do it again, right? Because what is this thing going to do? This is going to be applied again to the one on the right, which gives you the second R. You got the same thing again. One on the left gets applied to the one on the right. So basically you can make as many of these R's as you want. Let's do this in Notepad. I'm sure that'll clear things up. All right, so if we say YR, and let's say Y is equal to, what was it, lambda Y, lambda X, oops. I'll make sure I get this right. X dot Y. Okay. So if I apply this to R, then that mess gets applied to R. Now, I'm going to pause for a second. What happens if I took lambda X dot Y XX and I applied it to 5? What would we end up with? Can I do that? Is there a beta reduction there?
There should be a beta reduction, right? It'd be Y by 5.
Yep. On the left, it's a function, right? Where X is the input argument. And the beta reduction says, get rid of the lambda X dot, and you're stuck with Y by 5. That's all it is. And I'm doing it with 5 because when you see the larger, more complex pattern, sometimes you forget to think of it. It's just a thing, right? That's all it is. It's just a thing. 5 is just a thing. You know, you kind of have to visually start to think of this pattern as one block. It's easy to do with 5. What if I did it with something more complex? Lambda Z dot Z. What would I end up with? 2 copies of lambda Z dot Z, right? Basically what it's doing, it's saying, hey, whatever you give me, I'm going to give you 2 of them right back. But I'm going to throw an extra Y on the outside. So whatever you give me, I'm going to give you 2 of them right back. That's what it's doing. So when I take that lambda y dot lambda x y x x and I apply it to itself, remember what I'm saying, it's basically common sense rule is, whatever you give me, I'm going to give it back to you twice with a y on the outside. So if I take this and apply it to itself, I get y, and then I get 2 copies, just like before, 2 copies of the thing that you gave me. Well, what did you give me? You gave me a copy of me. And now I can do it again. This thing is saying, hey, give me something, and I'm going to give you back 2 copies. All right, I'm going to give you that. All right, but in addition to the 2 copies, I'm also going to give you an extra y out there. So when we do it again, I'm going to need this a lot. And it never stops, because this thing again is saying, give me something, I'll give you 2 copies with a y on the outside, and I'm going to get, and the thing that I give it is the same. How many do I need here? Does that make sense? This whole, first let me ask it in a couple phases. First of all, does it make sense that what this is saying is whatever you give me, I'm going to give you 2 of those back with a y on the outside? Does that make sense?
Yes, well, at least for me.
Yeah, okay. So that's what it's saying. Because you know, if it was just this, let's even make it simpler. Whoops, too simple. This is the simplest form, right? What does this say? Give me something, I'm just going to echo it back to you. Whatever you give me, I give you back. It's the identity function. And what is this saying? Whatever you give me, I'm going to give you 2 copies back. And then what is this saying? Whatever you give me, I'm giving you 2 copies back. Oh, but I'm going to put a y on the outside and enclose it in parentheses. So basically, we're going to make copy after copy after copy of y on the outside. And so when you put this thing inside the larger y combinator, we get that repetitive pattern on the inside. That's what this mess is. And on the outside, it's a function of, hey, give me something you want copied, which people tend to call R. So y applied to R is equal to that. And I need a couple of these. But once I do the beta reduction, okay, here's the outside argument. I'm just going to replace everything where I see a y. With an R. And then, same trick as we did a minute ago. What does that one on the left say? Whatever you give me, I'm going to give you 2 copies back. But now I'm going to put an R with outside the parentheses. And what am I giving it? That. So what do I end up with? That. And we do it again. And we can keep going forever. But if you look, what's happening here is YR is equal to that mess. If I wanted to, I could replace that as YR. And this is going to look really weird. And if it makes you more confused than less confused, then ignore that I did this. Because what's inside here? The thing inside here is equal to YR, right? That's what we said right there, equal to YR. So I could replace that, which means YR is equal to as many of these as you want. You can just keep making more and more copies. YR, YR, YR. What's the practical advantage of this in terms of developing math? Well, how do you develop in programming? How do you develop a complex function in programming or a complex program? Or have we not challenged you enough to do that?
I guess the first you writing out what it is and then the requirements. If you want to go down.
Okay, but once you get down to actually creating the code and you're making a complex function, I'm going to argue that you do this. When you write a complex piece of code, you don't write it all in like in C. You don't just write main and you have thousands of lines of code in main. You chunk up the job, right?
Oh, yeah, yes.
You say, oh, and you have a function that calls a function that calls a function, right? And that's called function composition. Right. So you have a large job to be done. That's what the code is doing. And it does it by doing a smaller job, a function that calls a smaller job, and a function that calls an even smaller job, and a function that calls an even smaller job. And that's called function composition. Or in math, you used to have this kind of thing, right? We have f of x, and we have g of x. Why am I capitalizing these? G of x. And then we can do this kind of thing. Right? What does that mean? It's function composition, right? And we can even do f of g, gosh darn it, Garfield, of h of x, if we wanted to. And we could keep going, right? That's function composition. Doesn't look like recursion yet, though, does it? If it was recursion, it would be f. I should just give in and do this. Right? Instead of applying two separate functions, using composition with two separate functions like f of g of x, why couldn't I make it where I run the function based on whatever that function returns? In other words, make it recursive. And instead of f and g and h, why not f and f and f, so that I'm actually recursively applying the same function over and over and over again. Well, guess what ours is, right? Right now, R is just a symbol. But what would be a meaningful way to replace R? If you replaced it with a function, I've got a function called on the result of this function being applied to this thing. And because we can do this as much as we want, we basically have recursive function composition. So we have numerals, we have Boolean values, we have mathematical operators, we have Boolean operators, we have if then else expressions to do selection in terms of what parts of the computation should be performed. And now we have recursion that allows computations to be performed repetitively. So we in a definitely not a formal proof way, but a nice casual way, we definitely have everything we need for a fully computational system. Now, next week, we're going to start with functional programming. And guess what? Functional programming looks like this. It's cleaned up, fortunately. This is so raw and pure and theoretical, but functional programming does look like this. How do you define a function? And you give it a function name. Whoops. You actually say Lambda input that would be a function. If you want to apply it to something, you apply it to something. That's how functional programming languages work. So this format is perfectly sensible if you're catching the patterns that we're talking about here. This is not very helpful, so we normally give it a name. I think that's right. And then I can say apply foo to 5. That's how we're going to get into that next week with Rocket, functional programming. It is a completely different way of thinking about how computation works, because we have trained you for years to think in terms of iteration, for loops and while loops. And now the only tool you have for repetition is recursion. So all the stuff that you used to think of iteratively, retrain you to think of it recursively. And we're going to spend, I think, 2 weeks on that module, because it takes a little time to dig into the language, and we're only skimming the surface of it. It's just enough to get you to think functionally. Okay, do we have questions?
Yeah. How do we again stop the recursion?
So then you have to have a clever definition for R, where once you start applying R to itself, the progress towards the stopping condition has to occur. So R will be something that would contain a Boolean test and an if-then-else structure in it. And no, I'm not going to I'm not going to show that. It's just going to be far too ugly.
Okay. Yeah.
Yeah. But hopefully you can conceptualize it, even if there's, without the concrete example.
Yeah.
Okay.
Some.
Okay. I will see you on Monday. Have your Dr. Racket stuff ready, please. Most of what's going to happen next week is just showing you, walking through code, because even though we're talking about some functional programming concepts, the easiest thing is to show code. I will have some slides, but it's mainly going to be about code. And I suspect next Friday we'll go back to office hours, but we'll see how it goes. All right. Have a great weekend.
You too. Thank you.
You too.